Mercury is the closest planet to the Sun. Its surface reaches 800 degrees Fahrenheit, hot enough to melt lead. And buried in craters just miles away, in permanent darkness, sit billions of tons of pure water ice. How is that possible? Mercury was supposed to be the simplest world in the solar system, a scorched rock in a tight orbit, stripped of anything worth studying. Almost none of that is true. The answer begins with something Mercury barely has: an axial tilt. Earth tilts at 23.5 degrees, which gives us seasons and ensures sunlight reaches every corner of the globe at some point during the year. Mercury tilts at nearly zero. Its axis is almost perfectly vertical. And because of that, there are craters near Mercury's poles, deep, ancient impact craters, whose floors have not seen a single photon of sunlight in billions of years. Imagine standing inside one of these craters. The sun is blinding on the surface just above you, close enough to blister exposed rock to 800 degrees. But where you stand, in the shadow of the crater wall, the temperature plunges to nearly -300 degrees Fahrenheit. No atmosphere carries the heat inward. No wind distributes warmth. The shadow is absolute. And within that shadow, ice survives. In 1991, Earth-based radar observations detected highly reflective patches at Mercury's poles, signals consistent with thick, pure water ice. 2 decades later, NASA's Messenger spacecraft confirmed it. Neutron spectrometer readings, laser altimeter data, and thermal models all converged on the same conclusion. Mercury's permanently shadowed craters contain between 100 billion and 1 trillion tons of frozen water. On the closest planet to the Sun. But the ice is only the beginning of Mercury's contradictions. And the strangest one has nothing to do with temperature. It has to do with reaching it. Look beneath the surface, and the structure of the planet itself makes no sense. Mercury is small, barely 3,000 miles across, only about 40% wider than Earth's moon. Yet it is extraordinarily dense, almost as dense as Earth, despite being a fraction of its size. The reason is its core. Mercury's iron core occupies roughly 85% of the professionally planet's radius. For comparison, Earth's core fills about 50%. Mercury is, in essence, a giant iron ball with a thin shell of rock wrapped around it. No other known planet in the solar system has proportions like this. Why? Scientists have debated this for decades. One hypothesis suggests that a catastrophic impact early in Mercury's history, a collision with another protoplanet, stripped away most of its original rocky mantle, leaving behind the dense metallic interior. A more recent theory, published in 2021, proposes that the Sun's powerful magnetic field during the early solar system drew iron-rich material inward, naturally concentrating more metal in the planets that formed closest to it. The question remains unresolved, and the European-Japanese mission Bepi-Colombo, expected to begin orbiting Mercury later this year, may finally provide the answer. And that oversized core is doing something extraordinary. It is still cooling. As the iron contracts, the entire planet shrinks, and the surface has nowhere to go but inward. The result is a network of massive cliffs, called lobate scarps, that stretch for hundreds of miles across Mercury's terrain. Some rise nearly 2 miles above the surrounding landscape. The largest, Enterprise Rupes, runs for over 600 miles, comparable in length to the San Andreas Fault. Messenger data suggests that Mercury's diameter may have decreased by as much as 7 miles since the planet formed, and the evidence indicates it has not stopped. Mercury is still shrinking today. If you could press your hand to the surface of Mercury at noon on the equator, the rock would be hot enough to melt lead. Wait for nightfall, and the same ground drops to nearly -300 degrees. A temperature swing of over 1,000 degrees Fahrenheit, the most extreme of any planet in the solar system. But Mercury's relationship with time is just as disorienting as its relationship with heat. The planet is locked in a 3-to-2 spin-orbit resonance with the Sun. It rotates 3 times on its axis for every 2 orbits it completes. The result is that a single solar day on Mercury, one full sunrise to sunrise cycle, lasts 176 Earth days. That is longer than its year, which is only 88 Earth days. A day on Mercury outlasts its own year. And during that long, slow rotation, the Sun does something no human has ever witnessed on any other world. Near perihelion, the point where Mercury is closest to the Sun, the planet's orbital speed briefly exceeds its rotational speed. If you were standing on the equator, you would watch the Sun rise, stop, reverse direction, set again, and then rise a second time before continuing across the sky. A double sunrise, the laws of orbital mechanics made visible. And yet, despite being our closest neighbor on average, Mercury is one of the hardest places in the solar system to reach. The problem is not distance, it is gravity. Any spacecraft traveling toward the inner solar system accelerates as it falls deeper into the Sun's gravitational well. By the time it reaches Mercury's orbit, it is moving far too fast to stop. Without a thick atmosphere for aerobraking, the only option is raw engine thrust. And the amount of energy required to slow down enough to enter orbit around Mercury exceeds the energy needed to escape the solar system entirely. The solution is time. NASA's Messenger spacecraft, launched in 2004, needed 6.5 years and a journey of nearly 5 billion miles before entering orbit in 2011. That route included 1 flyby of Earth, 2 of Venus, and 3 of Mercury itself. Each one a carefully calculated gravity assist designed to bleed off speed. Bepi Colombo, launched in 2018, is following an even longer path. 9 gravity assists over 8 years. Pluto, at the edge of the solar system, was reached in 9.5 years by a spacecraft that never slowed down. Mercury, 36 million miles from Earth, required almost the same time and multiple planetary detours just to park in orbit. This is Mercury's final paradox. The planet closest to us is one of the least explored worlds in the solar system. 3 missions in 50 years. 1 flyby. 1 orbiter. And 1 still on its way. We know more about the moons of Jupiter and the rings of Saturn than we know about the scarred, shrinking, ice-harboring world that orbits just next door. Mercury does not fit the story we expect. It is not the barren furnace the textbooks describe. It is a world built on contradiction, frozen and scorching, ancient and still changing, closer than anything and harder to reach than almost everything. And perhaps that is the real lesson. The things we assume we understand simply because they are nearby are often the things hiding the most.